Hello everybody, today we've got lecture slides on hypothesis testing using chi-square distributions. Okay, have you ever wondered whether your birthday affects your chances of being a Major League Baseball player or not? Have you ever wondered, do people buy snacks more often for certain types of movies, such as a thriller, comedy, or drama? Or is a particular dye fair? How would you know? Previously, new hypotheses tests required new test statistics. These tests require a new probability distribution. This is called the chi-squared distribution. A new continuous probability distribution notation should say chi-squared. It is distributed as chi-squared with the parameter of df. df stands for degrees of freedom. The parameters of this probability distribution are the mean is df, variance is 2 times df, and standard deviation is the square root of 2 times df. The probability density function, it gets closer and closer to the normal distribution. So I'll say approaches normal as df goes to infinity. It is skewed to the right, and it's different for each df. All right, now what is the goodness of fit test? So we talked about the new distribution, which is going to be very useful as we go through these tests, but now let's talk about the test. Okay, so imagine, this is just sort of some setup, some motivating example. Imagine you have data of at least nominal level with finitely many outcomes. So remember, nominal level is you don't have to be able to order it, there doesn't need to be differences, it could just be categorical. You have a sample of n data points of k different possible outcomes. So an example would be if I was rolling a 4-sided die as pictured in the top corner, and these were the results. This would give me a frequency table. If I rolled it 87 times, I get this frequency. This might not be uniformly distributed. Could I do a hypothesis test to determine whether this difference is random or if something is wrong with the die, systemically giving me bad data, is favoring the 2 for some reason? Or is it just the natural random fluctuations of my data? I will do a hypothesis test comparing it to the expected frequencies. Okay, goodness of fit test. Does data fit a discrete distribution? That's what we're talking about. N is the total number of samples. K is the number of outcomes. O is the list of observed. E is the list of expected. Here is the hypothesis test, all 8 steps. A goodness of fit test. Does my data fit a theoretical distribution? First thing you do is identify the claim, then you negate the claim or take the opposite of the claim. After that, you identify the null and alternative hypothesis. The null hypothesis is that the distribution of given data is as suspected. It's not that the distribution of the data is suspected. It's the underlying process that generated that data has a distribution as suspected. We know the distribution of the data, and it's clearly not the same as this. The frequency of the data is not the same as expected. But is the difference in the data sufficient to suggest the actual theoretical underlying process is flawed? That's what we're asking. It's not about the distribution of the data. It's the distribution of the generating process of the data. Okay, so if I took another sample, it would be different. The alternative hypothesis is the distribution is not as supposed. You'll notice chi-squared equals 0, chi-squared greater than 0. The chi-squared statistic, which we will introduce in step 5, is a measure of how different the data is from expected. Is if chi-squared equals 0, that means the data completely agrees with suspected, completely agrees, and that would suggest, as best as anything could, that the underlying process agrees with the suspected. The alternative is chi-squared is greater than 0. Chi-squared will never be negative, and so the opposite is just that chi-squared is greater than 0. Step 4, select significance level. Step 5, identify test statistic. Well, what is the test statistic? It's given to you. It's this chi-squared test statistic. We'll go over how that is calculated in the example. Step 6, find the p-value. The p-value is always right-tailed. Use a chi-squared distribution. Chi-squared distribution needs degrees of freedom. It's going to be k minus 1. All right. After you have found the p-value, you have to make a determination. Is that p-value less than alpha? If the p is low, the null must go. If not, we fail to reject the null hypothesis. Restate the decision in non-technical terms with reference to the original claim. There are requirements that ought to be met before you proceed. Make sure that the data is random. You have no guarantees about the conclusions to follow if the data is not randomly selected. If it's very biased, if it's very poorly collected data, then the theory that we're going to discuss won't apply. And the second requirement is that the data are frequency counts of a set of outcomes. And of course, we wouldn't be able to calculate anything if that weren't the case. Okay, and then for each outcome, expected, not observed, but expected frequency has to be at least 5. Okay, let's go over this example, which many of us are familiar with. So this is my spreadsheet that has the data. A spreadsheet like this one can be found on the Canvas home page for our course. Let's start our hypothesis test. Let me read the question. Absenteeism of college students from math classes is a major concern because missing class appears to increase the drop rate. To suppose a study was done to determine if the actual student absenteeism rate follows faculty perception. The faculty expected that a group of, that should be 500. I forgot to change that. 500. A group of 500 students would miss, according to this table. This is what was expected. So about 250, about half will miss 1 to 2 classes. 150 will miss 3 to 5 classes, and so on. A study was done, and 100 students were randomly selected. Their absences were found from data. Test the claim that the faculty perception is accurate. Step 1, original claim. The original claim is that the faculty perception is accurate. Now, I always want to write that just as I see it in the problem, because that original claim is going to guide my step 8, which is reporting it. I want to report it close to the question being asked. That's good policy. When somebody asks a question, give the answer in their words so that you make sure you answer it as faithfully as possible. All right. The opposite of the observed claim is the faculty is not accurate. As we talked about, this is equivalent to chi-squared equaling 0. The actual chi-squared, when we talk about hypothesis tests about mean, we're not talking about the data. We're talking about the actual mean. The actual chi-squared is going to be 0. That's our original claim. The alternative is that the chi-squared is greater than 0. Let's go to step 3. Our null hypothesis is that the perceived frequencies, and this is in general, right? The perceived frequencies agree with the actual frequencies. The alternative is they do not agree. Okay, now let's go to step 4. And this is going to be alpha. This is significance level. Alpha equals, I don't think a significance level was offered here. What's that going to be then? 0.05. Step 5, test statistic. What do we do? Roll test statistics. I need observed and expected frequencies. Those are given here. See, Command C, Command V. Paste that. These are the perceived, expected. Command C, Command V. Great. Copy and pasted it. Pasted these right. This is my E minus O, or O minus E squared divided by E equals parenthesis O minus E squared divided by E. Enter. Command C, shift, down, down, down. Command V, paste. And this is test statistics, so I'm going to say chi-squared equals this. And this is going to equal the sum. So I summed up for each outcome. There it is, 96.37, which is enormous. These are wildly off. Okay, let's carry on for demonstration's sake. Step 6 is to compute the p-value. The p-value equals chi-squared dis.rt. It's a right-tailed test. For the x, I'm going to push chi-squared. For the degrees of freedom, k minus 1. In this case, k is 5. There are 5 outcomes, so my degrees of freedom is 4. Enter. Yes. Super small, as I suspected. Step 7 is to make my conclusion. Is the p-value less than alpha? Yes, very much so. So I reject the null. Okay, step 8. What do I say then? My original claim is that faculty perception is accurate. I reject it, so there's sufficient evidence. There's sufficient evidence to warrant rejection of the claim that faculty perception absenteeism is accurate. Alrighty, so there it is. That's our hypothesis test. So something that looks like this is what you're going to want to give me on the exam, nothing less. And make sure that I am able to select each of these cells and see the formulas. How is the p-value computed? See, I can click on it and I can see exactly what function I can use. You will get very little credit if it just shows the number, like you copied and pasted it. If you don't do that, I want to see your formula and know what you're doing wrong if you're doing it wrong. All right, very good. Okay, that's great. Okay, so that's that. That's the absenteeism one. The faculty perception is not accurate. At this point, fill out these questions, please. I'll be looking on the slides. If these questions are not answered, you will lose points. Try and answer those. Now, a few words about Benford's law. The observation that the leftmost digit in real-world data follows the following distribution to the left. That's what Benford's law is. It's very interesting how that just sort of happens. Numbers with a leading of 1 occur with a frequency of 0.301. That's 31.3% of the time. So of your data set, you can expect about 30% of numbers begin with a 1. Isn't that something? On the other hand, numbers with a leading coefficient of 8, say, generally occur only 5.1% of the time. So they will begin with an 8 about 5% of the time. This phenomenon is used to detect fraudulent data that has been doctored in an individualized way will violate this Benford's law phenomenon, and that can be exploited. In the New York Times article, Malcolm Brown writes that the income tax agency of several nations in several states, including California, are using detection software to identify computer system intrusions. This software is based on Benford's law, as are a score of large companies and accounting businesses. So Benford's law is out there. People are using it. All right, anyway, we're going to do a Benford's law example at the end of this slide deck. Before that, I want to introduce another hypothesis test. This is called a test for independence. Do the variables affect each other? Now, here's the setup. So you have a sample. You have so many subjects. And what you do is you look at 2 variables. So you have a sample of categorical variables from n subjects. So such as two variables could be race and income. You have a contingency table. You count the number of people that fall into both categories. Then what you can do is you can test to see if one of the variables has an effect on the other. Is a particular race likely to have a higher income? That means that it affects it. It's not independent. So there's a dependency there. Okay, and so the question is, could the variables be statistically independent. A test for independence has notation. N is the number of samples or subjects. R is the number of categories. The number of rows is the number of categories in one variable. C is the number of columns. The categories in the other variable, a two-way table. O is the list, which is an array in this case, observed frequencies. And E is a list of the actual empirically determined expected. No, sorry. This one's empirical. This one here is more or less theoretical. And that's the expected frequencies. How do you come up with these expected frequencies? Each E is associated with a particular cell of the table. Each cell is in its own row and column. And so what you do is you take that row's sum, so the row total, you take that row total and you multiply it by whatever the column total that it is in. Multiply by the column total for that cell. And then you divide by the grand total. And that is your expected frequency for that cell. All right, let's take a look at that. Okay, and so that is how you find the expected. More on that later. Okay, test of independence. Do the variables affect each other? That's what we want to know. Okay, so again, you identify the claim, you negate the claim, you identify the null and alternative hypotheses, and what you do to do that is the null hypothesis is always going to be variables are statistically independent. We assume they are independent, no difference between expected and observed. And so chi-squared for that is going to equal 0. The alternative of that is that they are not statistically independent, and so chi-squared would be greater than 0. And again, this is not chi-squared using the data. When I write it here, I mean chi-squared of the actual sampling process, the true distribution of income versus race. Step 4 is to select the significance level, and step 5 is to identify the test statistic. And it is exactly the same as with a goodness of fit test. The only difference is that a goodness of fit test only had K categories. This one here is going to have R times C categories. You're going to have a term in this sum for each cell in the contingency table. Okay. That will be clear in the example. Next, you find the p-value. It's always right-tailed. In this case, though, the degrees of freedom is going to be R minus 1 times C minus 1. After you have the p-value, you need to make a determination. If the p is low, the null must go. Following that, you restate your decision in non-technical terms. In order for this to apply, the data must be randomly selected. Make your sample carefully. The data needs to be in a contingency or a two-way table. Now, for every cell in the table, the expected frequency must be at least 5. We don't want to deal with rare events. For the example, suppose we collect data from 600 people at a theater. We know the type of movie they saw and whether or not they bought snacks. Test the claim that whether or not a person buys snacks depends on the type of movie. So in this case, we have two variables. A binary variable, did you buy snacks or did you not? And a categorical variable, what type of movie did you watch? Action, comedy, family, or horror. Does whether they bought snacks depend on what movie they watched? Were they more likely to buy snacks for an action movie or a comedy rather than a family or a horror movie? That's what we want to determine. Okay, and so what we're going to do now is I'm going to get out my keyboard and we're going to go into Excel. We're going to work this problem out. Okay, snacks. So I go to example 2. Step 1, original claim. What was that again? Whether a person buys snacks depends on the type of movie. The original claim is that there is dependence there. Okay, so the claim is whether a person buys snacks depends on the movie A, C. Symbolically writing this, chi-squared equals 0. We are assuming they are dependent, and it does not behave as we would expect if random. My original claim is that chi-squared is greater than 0 because it can't be negative, but it's not 0. The opposite of the claim is whether a person buys snacks or not doesn't depend on the movie, saying they are behaving as though independent. Step 3 now, the null hypothesis is always, for these tests, chi-squared equals 0. The original claim was the alternative hypothesis is chi-squared greater than 0. Step 4. This would be that the two variables are independent. That is my null hypothesis in English. The two variables are statistically dependent. Step 4, alpha equals 0.05. Step 5. Okay, now this is what you've been waiting for. Step 5, first observed. Observed equals this table, Command C, Command V, expected, E equals. Now the reason I saved space is because I'm going to want the row totals and column totals. Row totes. Row totals, column totals, equals sum, enter, Command C, Shift over Command V. Now this one equals that. I could just do that plus that, couldn't I? There. I didn't even need to use the sum. Command C, Command C, Shift, down, Command V. It said there were 600 moviegoers, at least I think it did. Yeah, 600. So that's a good check. That box I have selected now is going to be the grand total. Now, let's find the expected distribution of this table. It is going to equal the row total times the column total. See, I'm in this first cell now. This first cell is going to correspond to the 50 here. I'm going to divide by the grand total. I need to put in some dollar signs. As I fill my table, I want the row total referenced not to change when I change my column. Because if I only change column, it is in the same row and therefore has the same row total. I don't want to change the column. The column is indicated by the letter. So I'm going to put a dollar sign in front of that letter D so that the letter does not change. Wait a minute, hold on. If the column changes, I don't want the column to change, so I'm going to go D, just as I thought. I kind of second-guessed myself. Now, when the row changes, I don't want the column total to change, so I'm going to fix that column. However, I do want the column to change if I change columns. So this B24 is my column total. And if I move this cell that gives me the expected frequency, if I change cells to a different column, I want that column total to change. Similarly, if I change rows, I want the row total to go to a different row. So I'm not going to put a dollar sign in front of the 20, which tells me the row. And so I'm not going to put a dollar sign in front of the B. But I will put a dollar sign in front of the D and the 24 because I never want the grand total to change. Okay, take a hard look at that. This is complicated stuff. Equals. There is my expected value for the first cell. Great. Command C, select all, Command V, and there are my expected frequencies. Command C, bring this over, Command V, so there's my row and column sums. What about these here? Equals this plus this equals 125. Command C, paste, and V. Wait a minute, well, that's wrong. Command C, Command V, Command V, Command V. 600 again. That gives me an indication I did it right. The grand total is always the same. It just tells you that if they were independent, this is the most likely arrangement for them. All right, so there's my observed. Put a border around that. And here's the expected. Put a border around that. All right. Now, what I need is, and I'm at a loss of words to put this. I'll put this right here. This is going to be my O minus squared divided by E equals, and that's going to go in this table here. Okay, I'm going to go equals, parenthesis, O minus E, close parenthesis, quantity squared, divided by E. I'll enter. No dollar signs. Command C, fill that in. Command V. The sum of the differences. The sum of the square of the differences divided by the expected. My test statistic chi-square equals the sum of all of this. All right, it's 65, which is quite high, especially because the degrees of freedom is 3, I think. I'm glad this is a video, so you can go back and look at all this. I hope the way we determined E and the chi-squared statistic makes sense. Feel free to come into office hours if it doesn't. Step 6 now is to find my p-value. The p-value equals chi-squared, right-tailed, test statistic, comma, degrees of freedom. df equals the row count, which is 4, number of rows equals 4 minus 1 times 2 minus 1. The number of rows minus 1 times the number of columns minus 1 gives me 3, so that's my degrees of freedom. So my chi-square distribution is going to have a mean at 3, and this is 65, so this p-value is going to be way small. Step 7, is p-value smaller than alpha? Is the p-value smaller than alpha? Yes, it certainly is, and so I reject the null. Step 8. Step 8, my original claim is that whether or not a person buys snack depends on the movie they see. Now, that was the original claim, but not the null hypothesis. The null hypothesis was that it does not depend. What we see here is some dependence going on here. It doesn't give us any insight as to what that dependence may be, but to say they are independent is a statistical absurdity. It's with probability 4.9 times 10 to the negative 14th. We rejected the fact that they are independent. There is sufficient evidence to suggest a dependence on whether a person purchases snacks and the movie they see. All right, great. Let's go to the next thing now. There was a dependence there. Here are a few more cues for you to answer. Again, I'll be looking at these. Interested to see what you have. This is the last test we'll be talking about. Nearly done. The test of homogeneity. Do two random variables have the same unknown distribution? We've got two discrete random variables. Do they have the same distribution? Here's an example. Do males and females live in dormitory apartment or with parents at pretty much the same rate, or do they not? This is exactly the same as a contingency table test, just the interpretation's a little bit different. Okay, so test for homogeneity. Do two discrete random variables have the same unknown probability distribution? The interpretation is different, but the way you do it is the same. Could the distributions be from the same population? N is the total number of samples. R equals 2. It's the number of rows. Each population has its own row. C is the number of columns. O is the list of observed. E is the list of expected. The expected value for each cell is the row total. Each cell is in a column. The total of that column goes here. No cell is going to have the same row or column table. This number is unique to a particular cell. And then here we have grand total. Here's the test for homogeneity. Exactly the same as the test for independence. Everything else is exactly the same. I copied and pasted it and changed nothing. The requirements are exactly the same. The data needs to be random. The frequency counts need to be a part of a contingency table. And the expected frequency must not be less than 5. Here's the example. This is used from actual data that I got from the Pew Research website. I'm beginning to use my own data now. Well, that I get myself. Okay, example 3. Is there a political right and left? In a Friday forum, it was suggested that the political right and left is a myth. So they said the myth of the left and the right. One way of looking at this is to test whether those who self-identify as either right or left actually feel the same about certain issues. So if on average they feel the same about certain issues, then there really isn't much of a difference between them. And that supports this idea that there isn't a right and a left. This is not exactly what the speaker, I believe, said, that rather than there being one spectrum, one dimension in which you can neatly divide people, there are a multitude of dimensions. And this doesn't exactly speak to that, but it's an interesting question nonetheless. Okay, so the data below is from a Pew Research study from 2021. When asked, how would you rate economic conditions in this country today, the responses were observed. Okay, so 10 people from the right said excellent. 329 said good, only fair was said by 996 people who identified as being from the right, and so on. The test claimed that the distribution of sentiment is the same across the political spectrum. Let's see if the p-value is going to be, if the test statistic is going to continue to be super. What do I do now? Okay, tab, there we go. All right, so now I go to right and left. Step 1. Okay, we'll just go back to it. What was it again? A test that claimed the distribution sentiment is the same. The distribution of the strength of the economy, there it is, does not depend on political ideology. Copy that, Command C. Now I'm going to do step 2, Command V. Oh, it didn't work. I need to go in here and put OC anyway. Original claim. All right, now I'm going to copy this cell. Okay, come here. There it is. This is the opposite of the original claim. The distribution of perceived strength of the economy does depend. This one is chi-square equals 0. This one's chi-square is greater than 0. Step 3 is the null hypothesis is going to be chi-square equals, which basically means independent, or they're a homogeneous. These are homogeneous distributions, meaning their distribution is shared. And then chi-squared is the alternative, is that it is greater than 0, meaning they are not homogeneous, not the same distribution. Step 4 is alpha. Is alpha given this time? Nope. 0.05. Step 5. This is the test statistic. We need observed, and those are here. Okay, then I'm going to need totals. So column totals and row totals equals sum, enter, Command C, shift, over, Command V, paste. Now equals sum, enter, there's that, Command C, Command V, one more, Command V. So 8,468 people were polled by this Pew Research study. All right, let's compute the expected. So here's the original data, and I'm going to be filling in this box of expected data. This thing is going to equal the row total times the column total divided by the grand total. Let's put in some dollar signs so I can fill it, and the appropriate things will change. The row total, I want that to change if I change rows. I don't want it to change if I change columns. So the column designation, which is D, must stay the same. Now the column total, I don't want it to change when I change rows, because it's in the same column if I only change rows. So I don't want it to change if I change rows. The row designation is the number, so I'm going to put a $sign in front of the number. Now the grand total, I don't want it to change. Freeze that whole cell. Enter. Command C, copy that. Fill all that in. Command V. There it is. Test the grand total here. Equals sum of them all. Perfect. That looks pretty good. Over here is going to be O minus E squared over E equals O minus E squared over E. Enter. Populate. Whoops. Command C. 4 columns, 2 rows. Command V. And there it is. So that's all those differences. Now, my test statistic is chi-squared equals, oh, it's enormous. I need some better examples. One's closer to the same distribution. Okay, equals the sum, there it is, 299. It's very big. Wait, something was wrong here. That's exactly what it needs to be. Funny that it's the same numbers. All right, step 6, p-value equals, let's compute the p-value. We need practice to really learn how it's done. Equals chi-squared dot dis. There it is. Degrees of freedom is 3 again. 3 and enter. To the negative 64th. That's small. Step 7. P-value less than alpha. Oh yeah. Reject the null. Step 8. There is sufficient evidence to suspect. There is sufficient evidence to suggest that, let's see, what's the original claim again? The perceived strength of the economy does depend. To suggest that the strength of the economy on political ideology. All right, very good. Okay, what do I do with that now? Go back to notability. All right, just one more cue. I'm going to end this video now, and I'll do the example videos later. Okay, everybody, have a wonderful day, and good luck.